Hey, so I hope you're having a good day. It is actually almost midday here on Tuesday. I totally forgot I had to make a video. This morning I woke up and I was like, oh, I have to do a video. But I was actually a good student. I did homework first. I was like, get some homework done, then come back to the video. Doing homework, going well. All of a sudden I realized I have 50 minutes until noon. I should probably figure out my video. So here I am. I want to talk about math I get to do in college that is kind of way better than math I did in high school. I started doing math for my thermodynamics class that you can't do with a computer. I think generally there's two types of math that doesn't work on a computer. There's the ones that's just tricky. There's the ones that's like a computer could do it if it knew what to look for. There's just, it doesn't have the pattern recognition and the logic to figure out the method it should be using to solve it. And then there's another side to it, which is vastly more entertaining, which is the numbers are too big. So I'm doing like statistics and entropy. Basically, you can think of a solid, let me find a solid. A solid object is made up of atoms. That's not too hard. And you can imagine all of those atoms attached to other atoms by springs in like a crystal structure. Each atom has a bunch of springs that it can store energy in, that it can be like bouncing this way, or this way, or this way, or in a combination of all three. And you can think of those springs as having units of energy because energy is quantized at a small scale, it doesn't matter. You can look at this and say, oh, it's got a bunch of these springs, and these springs can have, and then it's got a bunch of these little energy bits that are dispersed throughout the springs. And then you say, oh, okay, so how many different ways are there for these energy units to be dispersed throughout all of these springs holding these atoms together? And the formula for this is called the multiplicity of a state. Basically, how many different ways can we distribute n number of energy units within x number of oscillators of springs. And that function has a factorial in it. If you don't know what a factorial is, it's a number times the number minus 1 times the number minus 2, all the way to 1. So like factorial 3 is 3 times 2 times 1, 6. Factorial 5 is 5 times 4 times 3 times 2 times 1, which is 120. 10 factorial, 3,628,800. So you can see that pretty quickly factorials get huge. And then I'll get a problem that's like, hey, there's 1,000 springs in this solid, which, to be fair, hugely small, right? That's like 300 atoms. But 1,000 factorial is much bigger than that. So I get an overflow error. When we get asked these questions on the homework, we're put in this really, I think, fun position of saying, you can't plug this into a calculator because the numbers are too big, which almost makes me feel pride as a person because I get to go through, right? And so you've got this formula for the multiplicity that's not just 1,000 factorial. It'll be like 1,000 factorial over the product of 400 factorial and 600 factorial. And you go through and you figure out, okay, what does this mean? How can I cancel stuff out? How can I get to a point where I can solve this answer easily? I have to take this number, this function that has a numerator way bigger and a denominator way bigger than the calculator can hope to ever hold in its memory, and I have to convert it into something that it could hold in its memory, so that way I can get an answer. There's like also approximations of like, oh, something x factorial is approximated with this function that's like x to the x, which is also unreasonably big for your calculator, right? It is also, at the end of the day, very close to the same value as the factorial, but it is in such a way that you can be combining exponents, and basically you get it to a point where you get a value that is less than 1 to the power of 1,000, which your calculator can do, because any power that's less than 1 will diminish in size instead of increase. Very cool, very fun. No idea how much of this made sense. Maybe I can do a video that's like, hey, this is actual math behind it. I just wanted to get the general idea across that I enjoy math, and I enjoy feeling like I can do something a computer can't. Asa, I'll see you on Thursday. Wednesday. Today's Tuesday. We're playing D&D today, a day early, so I think it's Wednesday. Have a great Tuesday, Asa, and I'll see you on Wednesday.